bit awkward. Let's see if we can turn it on.
Just push and keep while
There we go.
Yeah,
Yes.
we can
Can
hear
you
you.
hear me now? How are you all doing?
Fine, thanks.
Yeah? You're not tired yet? So, my name is Radek Simko. I work for HashiCorp. And you can also find me on the internet as Radek Simko, pretty much everywhere. GitHub is probably the most relevant to this talk. I work as part of the Terraform team, maintaining the provider land, mainly AWS, but I also build the Kubernetes provider, which is what we're going to talk about today. So just a quick show of hands. This is going to be a bit more intimate, which is, that's more interesting because I can get to see who uses Kubernetes. Okay, just 3 hands. Who uses Terraform? Okay, that's 6. That's good amount. So managing a Kubernetes cluster means managing a few different layers to me. So let me decompose the whole thing into 3 layers. First, we start with something I call base infrastructure. That's depending on where you run, that could mean something like IPC, your network, your firewalls, EC2, VPN, CDN, etc., etc. And then on top of that, you expose some kind of interface through operating systems, like your favorite flavor of Linux. And there you basically set up things like etcd, kubelet, the API server, network overlay, CA certificates, kubetns, etc. And generally install Kubernetes. And then once you have that, and basically you can use tools like Puppet, which are Ansible, to achieve that. And once you have that, you get to the third layer, which is Kubernetes, which involves things like persistent volumes, replication controllers, pods, etc. And now, many people have been using historically Terraform to manage the lower part, and you can still do that. But what I'm going to focus on today is the top layer. That's the API, Kubernetes API. And obviously there is an overlap in every direction. There is no clear answer or like right or wrong solution why you should or should not be using any particular tool to manage any particular layer. But let's just say what we're gonna talk about. So just a quick disclaimer: every company has different needs and workflows. So not gonna try to convince you that Terraform is the only way to manage Kubernetes, because it isn't. So read that as that there is no silver bullet. So as we dive into the content of this talk, I'm going to cover HCL. That's the language that Terraform uses. The nature of the workload that you can and perhaps should run through Terraform. And one of the benefits of Terraform, synchronicity. Why covering the full life cycle is probably a good idea. And then we're going to have a look at where is the responsibility overlap between perhaps the existing tooling around Kubernetes and Terraform. And if we have some time, we're going to get to demo. So HCL, so-called HashiCorp config language. Is anyone familiar with HCL already? A few hands. So HCL, even if you're not using Terraform to manage your infrastructure, if we set the manual management aside, because that usually doesn't scale, you would be building your own scripts using a high-level language like Python or Go. And that means you would need to deal with all of the idiosyncrasies and nitty-gritty details of the APIs, and generally use an imperative language. And at the end, you would probably ask for some help from the data languages, like JSON or YAML. because hard coding all of the details of the infrastructure in a programming language like Python or Go doesn't seem like a very scalable model. And those languages on the left side, like Python or Go, offer you plenty of ways to shoot yourselves in the foot. They have classes, functions, for loops, etc. Whereas on the other side, data languages, because they were designed to transfer data, they don't have any of these features. So they are very much simpler. But they also lack features that you may find useful when describing infrastructure, like referencing or comments. I mean, you can do referencing in YAML, but have you ever tried to do that? If you tried, then it's probably not a great experience. So that's why, despite that designing a DSL is a challenge, that's why Puppet and Terraform have chosen that path. So HCL is a separate project which you can find on GitHub, and it is used in various HashiCorp projects like Console, Vault, Nomad, or Terraform. The nice benefit of HCL is that it's JSON compatible, which is useful for generating code. You may ask, why would I want to generate the code? So one of the reasons, well, here's an example. It's a repository managed by the GDS, that's Government Digital Service in the UK. And they take advantage of this in their solution for DNS management. So they take their bind zone files for DNS, they convert that over to JSON, and then hand it over to Terraform, and Terraform creates DNS records in GCP, Google Cloud Platform, DNS, and Route 53. So that's how they manage their DNS to make sure of the redundancy. Now, coming up, workload. By the way, if you have any questions in the meantime, feel free to raise your hand and ask. So what kind of workload, Kubernetes workload, is best managed by Terraform? So the Kubernetes provider today supports, I think it's 13 resources and 2 data sources. And it's a long list, but those are all V1 resources. And I'm going to cover the sort of alpha and beta later on. So there are some ops-focused resources on the list, resources that would be typically used by operators rather than developers, which involves config map, limit range, resource quota, secret namespace, which allows you to sort of scope down your workload or service accounts. In case, I'm hoping that most of you are kind of familiar with this. No need to go too much into detail what each of these resources mean. So operators are already likely familiar with Terraform, and they are responsible for bringing up the clusters. So this is why it's a good fit. Now we come to ops workload. There are some workload resources like pod or replication controller, which basically replicates pods, or horizontal pod autoscaler, which tells the replication controller how to replicate the pods, or the service, which exposes your pod to the internet, to the users basically, or to other services. And while you could use those resources, right, you could manage those resources as a developer to schedule your application workload, I wouldn't recommend you do that. Instead, I would suggest that you only leave these resources for ops, and the reason for that is because Kubernetes has this concept of admission controllers, where the controller which sits in Kubernetes can intercept a request for the creation of the resource and modify the resource and give it back to you in completely modified, and it looks completely different. And that doesn't play very well with the way Terraform works, because in Terraform whenever it tries to create a resource, it expects the resource to come back in exactly the same state. And it is kind of a feature of Terraform to detect any drifts whenever someone modifies the resource outside of Terraform. So that's why I'm suggesting that it should be operators who use these resources, because those are the people who are familiar with any admission controls that may be in the cluster. So that's workload. Now synchronicity. Kubernetes API is designed to be asynchronous, which enables scalability. So that's great, right? And Kubernetes always expects you to be sort of proactive about asking whether an operation has failed or finished generally, at least initially. But not all failures are retrievable. So let's have a look behind the scenes for a moment. This is a config let's see if I can use this. So we have a resource here. It basically describes a pod in a Terraform config. This just says that it's a pod. This is a reference name, so that you can reference the resource elsewhere in the config. This is the actual name that gets submitted to the API. This basically makes doesn't reach any API. That's just for internal reference. So that's the difference. And this is the spec of the pod, where we say we want to launch Nginx 1.7 and the name of the container. So now, what really happens behind the scenes, though, is that the Docker needs to pull down the image and start the container, which takes time, usually. And as you can see, we have a typo here. Mm-hmm. And if you have a typo, do you really want to, you probably want to know that you made a typo. So a single container failing because of lack of capacity probably doesn't matter unless it's the only one. So if you fail to launch the container and it's the only container that you have in the pod, then it's probably a problem. So that's why, oh actually, let me do the comparison. So this is how you create a pod in kubectl. You basically call kubectl create and the YAML definition of the pod. Then you ask for the status of the pod, because again, as I said, you have to be proactive. And then eventually you ask the events API, what's the current status? Why is it actually failing? Has it finished yet? Why is it failing? So you gotta ask for that. And in case of Terraform, what we do in the provider or in the resource is that we poll the API periodically for some amount of time, and we give you the reason why it has failed. So you don't have to do all of that sort of hard work. So now obviously I'm gonna cover the differences between replication controller and pods, etc. And in which case you would see the error, but in this case it's a pod. So as I said, if the single container in the pod fails, then it's a failure. So this is how you create a service in kubectl. Again, you pass the YAML config, then you ask for the status of the service, because the service needs to create a load balancer, and it needs to wait for the external API to come back from the API. So that takes some time, obviously, and the provisioning may fail as well, because you may run into limits, some quotas that your cloud provider has in place, and you would be checking the API again to see what's the current status. Here we would see that it has failed to create a load balancer because we have reached the limit of static addresses in GCP. So it may happen. Failures do happen. And once we reach the once we bump the limit, then we can we basically still need to wait for Kubernetes to reconcile and until it returns us the hosting or the IP, so that we can reference it elsewhere, which you can do in Terraform fairly easily. So here is an example of a config for a Kubernetes service. Again, fairly simple. What's different here, or what's new perhaps for you to see is this reference syntax here. What that means is that basically it draws a dependency between Kubernetes pod and the service, and it says create the pod first, and once you have the pod in place, once it's been created, then give me the app label and use it here. So that's the reference syntax. And then we have the port forwarding below, and we set the type to load balancer, which means the service will be exposed to a load balancer. And then that's the benefit that you get. You can reference the service, the load balancer that comes out of the service, which was provisioned by Kubernetes. You can reference either the hostname or the IP address in a DNS record in root 53, for example. Terraform will wait until the service, until Kubernetes has finished the provisioning of the load balancers, so that you can get the IP or the hostname and create the record, because you can't create the DNS without an IP or the hostname. So how does Terraform create this service? You run apply, and eventually it may time out. And the colors are probably not great, but it works the same way as pod. So if it fails, we query the event log to give you the reason of why of the failure. That's what you get. Now here is a successful service creation in Terraform, where you get to see the ordering. So once we run apply, which means Terraform takes all the configs and it sends all of the API requests in the right ordering, and you can notice that here we start creating the service, and it waits for the service to actually finish the creation, which happens here after about a minute. And then after that, we start creating the DNS record, and we use the IP address, which was pulled out of the service in here. But we didn't really have the IP address until this point. And then eventually we finish syncing the DNS record. So, full lifecycle coverage. Why covering the whole lifecycle is probably important or useful? Well, because every app needs to be created, updated, and will be eventually decommissioned. Because app is not done until it's decommissioned. So many folks believe that this is the path to production. We just create stuff and that's done, right? And in fact, you need to keep updating it, and one day you need to delete it. And the nice benefit of Terraform is that you get the full, you get one command to apply all the changes. It doesn't matter if you're deleting or modifying or creating resources. Terraform will try to figure out what needs to happen on the API level based on how you change the config. So we will hopefully see that in the demo, in more practice. And it's always advisable to see the plan, which basically tells you what's going to happen before it's actually going to happen. So yeah, that's the full life cycle. First we create, then we update, and we can delete. But whether the resource is updatable often depends on the field. So in case of a service, not every field that you can see here is mutable field. So in order to know which field is mutable and isn't, one has to read the docs carefully or hope for the best. So here is an example of updating a mutable field. That's the selector, which can be mutated. So you get to see that in the plan. So it's all in yellow, which basically means, yeah, it's fine. Terraform's saying, I can modify that without an outage. Shouldn't be destructive. Whereas here, you can see a different change. Cluster IP, which isn't mutable field, you can't just change a cluster IP. So in order to change the cluster IP, Terraform needs to recreate the resource from scratch. So that's what it says here. It says first is new resource, and it basically tells you, hey, something may go wrong eventually, because you're going to delete the resource and there won't be any resource for a short period of time. But the good thing is that you know this ahead of time, before things actually happen, before you run out of line. Now let's talk about where we draw the line between Kubernetes and Terraform.
I have a question.
Yes.
Can you use option create before delete on Kubernetes?
Yes, you certainly can. So there is so by default, what happens? What would happen in this case? If you had the config that we've seen here, just as is, it would first delete the resource and then create a new one. The reason Terraform does that is because your resource may have a unique name and it can't create the new one before deleting the old one. But if you already know that you use unique names, randomly generated, or at least some suffixes or prefixes, then you can use the lifecycle stanza in the config, which basically says create before destroy, which is what you're mentioning. So that's available to any resource throughout all Terraform, all providers, everywhere, which basically says reverse the ordering and first create a new one and then delete the old one. And basically after it creates the new one, it will also update all references and then delete the old one. So that's the sort of non-destructive way of updating it, I guess. Does that answer your question?
Yeah, thank you.
If you have any questions, just don't be shy. I'll come train with you.
So let's talk about the line between Kubernetes and Terraform. There are four main areas where you may see the overlap. So just because you can do something in either Terraform or kubectl or any other tool doesn't mean you always should. Annotations is one place. And it's Terraform's expectation often that, as I said at the beginning, what you submit to the API is what you get back. Or at the very least, it's clear what aspect of the resource may change over time. But that's not the case for internal Kubernetes annotations. Kubernetes has these annotations, which begin with kubernetes.io. And in Kubernetes world, these can be used to enable alpha or beta features, but they can also be attached by Kubernetes, the kubelet, to enrich some resources. Like, for example, to say what region or zone am I running in. And so there is no clear line between what's user-defined and what's Kubernetes managed, which makes it quite hard for Terraform to figure out the difference during the plan stage. Which is why we ignore these annotations in Terraform. However, there is demand for internal annotations, so we're going to need to figure out how to. We're going to need to revisit that decision and figure out how to support that. So container workload is another area of overlap. And you may run a static app in a single pod, excuse me. And you could schedule the standalone containers, but that's Terraform's Docker provider. So if you use Terraform Kubernetes provider, you could use Terraform to schedule the pod. And then within the pod, you would have those containers which are completely managed by Kubernetes. So Terraform doesn't care about any container that runs within the pod. That's the responsibility of Kubernetes. But in this case, Terraform can provide the initial feedback. Initial means when you first create the pod, because you probably, if you're creating a pod, then you want to know if it's actually running. Now we get to see more dynamic app where we can control replication controller through Terraform. And here Terraform schedules the controller and leaves pod and the containers to Kubernetes. So again, Terraform only cares about the controller and leaves pod and containers to Kubernetes. And it wouldn't even make sense to deal with pod failures at this stage, because you could have so many pods that just failures are expected on that level. So we don't try to mess up with that. And then you get even more dynamic, where you have those horizontal pod autoscalers, where you define the minimal and maximum number of pods that needs to run in the replication controller, which also needs to be managed by Terraform, because it doesn't need to be, but in this case it probably should be, because you get to define the initial number of replicas and need to reference it in the autoscaler. And there is a bit of overlap, because you need to define, as I said, the initial number of replicas, and then let Kubernetes manage the runtime, which means pod and containers. So one way to deal with this overlap is to use this lifecycle block that we talked about earlier. Other than create before destroy, it also has this other config option here, which is called ignore changes. And what we say here is, create me a replication controller with 3 replicas to start with, and then whatever changes happen to it, I just don't care. Like, just ignore any changes that Kubernetes makes or anyone else makes to that field here. So don't generate any diffs. So that will prevent the conflict. Now, volumes can be managed by Terraform. By volumes, I mean EBS or Google Cloud persistent disks. That's been always the case. But whether you want to use Terraform to manage those depends on your workload and trust between your operations team and the dev team. So more commonly, people who run Kubernetes are a bit more relaxed in the relationship between ops and devs, and they demand easy scalability. So you would let the storage class in Kubernetes to be managed by Terraform, and then storage class in Kubernetes would provision the EBS volumes or PDs on demand effectively. So you would just tell what kind of storage is you want. And you could do the same with persistent volume, which basically does the same thing, or persistent volume claim. Or even a pod, which may be a standalone pod, or a pod that is scheduled as part of the replication control. Now you can manage load balancers directly in Terraform and turn all the knobs there, but it may not be as convenient if you have more dynamic workload, where in Kubernetes your services just come up and go away very often, and you need to have them under the load balancer all the time. You need to have a load balancer per service. So in such case, it's probably more sensible to leverage Kubernetes for the ELB and Google Cloud load balancer provisioning, and then only let Terraform talk to the service, to the Kubernetes API. So we are pretty much near the end. We get to see the demo, hopefully find it. But yeah, before we dive into demo, or find it, we have two personas in the demo. The first one is developer Bob and operator Alice. And we're gonna build an on-call app. So Bob, who is the guy on the platform engineering team, is going to use Minikube. That's the sort of minified version of Kubernetes, which you can run in VirtualBox locally. And he's going to leverage the replication controller and the service. So let's see if we can. Any questions in the meantime?
Any questions? Just fill the pause.
Too many. Can you see that? Can everyone see that from the back? Yes? Let's see if we have anything in existing state. In fact, let me see if we have Minikube running. That's safe, that's not running, so Minikube start. Start Minikube first. That's why this isn't working. And eventually, when it starts, you'll be able to schedule something. In fact, I should perhaps spin up the GKE cluster as well. Okay, that's now. And it's still hopefully on. Huh? It's not running. Do I have it? Oh, that's because I don't have internet here. That might be why. Does anyone know how do I connect?
Yes, please see on the wall.
No, okay. Spot for me. That goes to the recording, right?
Yes. I can pause it if you'd like. Nothing to shame, I believe.
Right. There we go. That's better. Okay, so we have cluster running. Now we have Minikube running. Yay! Now that we have Minikube, let's see if just these tiny things that I have here. And start from, just let's review the configs that we have here. So we have the provider block here, which in Terraform basically says how to connect to the provider, which in this case is Kubernetes. Here we say which config context to choose. In this case it's Minikube, so basically connect to Minikube. Then we define the controller here. And we give it some labels so that we can address the pod through the service. Can direct the traffic. And then here we use our special service, we give the container a name, It's basically the Docker image which you pull down off the Docker Hub, and then we specify some resources. Limits in this case, so how far you can get, and then how much do we request at first. And then we have the service defined here, which in this case we use the cluster IP type because we run on Minikube, as I said before, so we don't have the load balancers available there. So that's why we have to just do simple IP forwarding. And then we also output the service name, which is very useful for either for the user or for someone else that may be leveraging your configs elsewhere. So let's run Terraform plan. And in this case, you can see that's fairly simple plan. Only 2 green resources, 2 to add, because there's nothing at the moment. I'm just going to run Terraform apply. And yeah, eventually, if I do not have speaking level. Okay, here we go. And now what I can do in Minikube, there is Minikube service, I think it's this way, Terraform output service name, like this. And that will hopefully bring it up. Maybe not. That should bring it up in the browser, unless I'm mistaken. Let's see what this does. Yeah, I just did specify. Service list. Right, that's the list. And the name of our service is this one. So that exists. I don't know why is it not coming up. Oh, that's just URL. Let's see. Maybe that goes here. No, that's just demo guts here. In effect. Anyway, I can
Probably
hopefully.
because of no fork.
No port. That's right. I should probably read sometimes what it says in the terminal. Yes, we don't have node port. So we need to define the node port. And let's see what the documentation says, which actually I wrote. It's a service. So node port. Yeah, that's in the port. So let's allocate node port. Let's give it a high port, something like this. Let's see. Different plan. Okay, you can change that. But it needs to be a different type, which is node port, I assume. Yes. That's why. So I think it can actually allocate the node port. So I just one type. Let's see. Yay! Yes. So this is the on-call app. It's the very first iteration. You know, the next one will have some PagerDuty integration. Now it just says I'm on call. We'll get there eventually. So that's the first persona. So Bob's done with his work, and now we coming up with Alice. And Alice has chosen the GKE cluster because she's an operator. So you know, GKE is the hosted Kubernetes service from Google, where they manage Kubernetes master for you, so it's much easier. And she's going to create some namespaces and limit ranges. So let's. So here we have the infrastructure. The cluster is already running because spinning up the cluster takes a few minutes, and I personally like watching the terminal and waiting for things to happen, but I gathered that not everyone's like me, so I just did that beforehand. So let's see. So this is what I've done before. We have the global container cluster. We have the provider. Yeah, that's in a separate file. But we don't need to see that. Here we have just the container cluster. We give it a name. I usually like to name my clusters in a way that it scares everyone away, so they don't delete my cluster. And then then we just generate a username and password and give it some permissions, and output the zone and the cluster name. And now the nice thing about G-Cloud CLI is that you can basically get the credentials for the cluster like this. So Terraform has this nice command that's called output, which basically lists all the outputs that you have defined in your configs, like here. Or you can reference any existing resources and stuff. So maybe just to explain for those of you who are not familiar with Terraform, this basically means go and look for a resource that's called like this. There's a type of the resource, and then the reference name, primary in this case, as the second after the first dot, and then the last one is the field name. And then we expose that in here. So you get to see that after apply and in here, Terraform output. So we hopefully have, let's see, kubectl. Let's see if we have access to the cluster. Does it list nodes? Or get nodes, kubectl get nodes. Hopefully. Yes, okay. So kubectl can talk to my cluster, that's a good sign. And now we can get to the meaty part. And those are the Kubernetes configs. So here we have Alice, who obviously runs the cluster, so she points her provider to the GKE cluster. And she creates the namespace, gives it a name, and then she creates the limit range, which basically says how much resources can a given pod scheduled in this namespace consume. So how much CPU and how much memory. So that's how operator can define boundaries within the cluster. Oh, yes, and this is, so basically I now need to download the Kubernetes provider, but since I only have that locally compiled, it doesn't actually do anything, but it just records the hash. So this allows us to actually ship. This feature came out in the recent major version, the 0.10 Terraform, and that allowed us to, instead of shipping one giant binary of Terraform, we now ship each provider separately, which rapidly increased the speed in which we ship new releases for every provider, so we don't have to ship like a whole giant release, just because AWS was so active, the AWS provider. So now we have Kubernetes provider in place in our plan, and again that's a fairly simple plan that we can review. We also get to see all the defaults that are not visible in the config. That's funny. So it says that this will be computed after the creation. So you can reference things like UIDs or IDs. Yes, so Terraform apply. Let's do that. And that's done. So what's next? Production. So we have production. I'm going to go live. Actually, these strikes first. So what we have here, now because Bob and Alice came together, they said, oh, our configs look very similar, but actually they are quite different. So what they need to do is to make sure that these configs are reusable, and one way to do that is to use workspaces and conditionals in those configs. So they agreed that they're going to use Minikube locally to test everything before it goes to the GKE cluster. And so they're going to use separate workspaces. Even if you have never used workspaces in Terraform, you are already using workspace, which is just called default. Now let's see what's the list. Just going to select default. And the reason workspaces exist is so that you can separate out the state of your infrastructure, in this case Kubernetes resources, so that whenever you can see that I deleted those resources previously, but in fact you can see that they exist here. You can still see that it's refreshing. So I'm going to destroy this again, but it looks like I'm doing the same thing. But in fact, I'm destroying those resources in Minikube now, because previously I was in the prod workspace, which was pointing to GKE cluster. So now that I'm in the default workspace, it means that in this config here, this conditional here, it's basically choosing the Minikube context out of the config. And if not, which is the prod workspace, it chooses the GKE cluster. And then we have, that's all the same business here. And we also have one other difference. That's how we launch the service. Because in GKE, we get to leverage the load balancers from GCE. And we don't have the chance to do that in Minikube. So that's why we have this other condition here. So let's see. So now we are in Terraform workspaces. We are in default. So that should work pretty much the same way as it did in the first demo. Let's see if we... oh, right, that's because obviously my kubectl is pointing to the GKE cluster. So I would need to credentials something. There's kubectl subcommand for managing credentials and switching the context, which I obviously don't remember. Does anyone know of that?
Config get context.
Get context is one.
Config.
Config.
Texts. I mean,
Yes.
get contexts. I can type.
Yeah, get context. Like that?
Yeah, but config should remain.
Like that?
Yeah.
Awesome, thank you. That's why it's useful.
Then config use context in
That's the one. Awesome, thanks for the help. You're gonna get a sticker. I have a special sticker just for Saint-Petersburg.
Great.
So Minikube service Terraform output service thing. Yes. Isn't that awesome? And now we get to launch that on the GKE cluster. So we just switch to workspace and select prod. Now we switch to workspace. And as you can see, The type is load balancer in this case, so we're going to wait for the load balancer to actually finish provisioning. So this will take a while. It will definitely take longer than the previous run because we are waiting for the GCP load balancer to finish the provisioning. So there is time for questions. Or we can just carefully watch the demo. I like doing that.
So, any questions? Yeah, I see.
Hi, actually I have a question not about Kubernetes and Terraform, but purely about Terraform. I wanted to know what new features are you planning to add in the near future, like in maybe 0.11 version, something cool that we can use and that will.
So as I mentioned, and as you probably already know if you're familiar with Terraform, there was the provider split. So if we are talking about the core of Terraform, where the next major version is 0.11, there are some things coming up. I'm not sure I can say that on the recording, we are, let's see how I can say that. We are well aware of some shortcomings of the language used in Terraform, that's HCL. We are hopefully going to address that very soon, or at least some of the shortcomings. So that's one area. I'm not part of the core team. Specifically, we have two people who work mainly on the core stuff. That's like Terraform's core. I'm mainly focused on AWS, so I can talk about AWS provider because we also schedule some work per provider. And the way it works in the provider land, at least for me, is that I basically take all the PRs and the issues, rate them, sort them by number of upvotes that the community has given us, and then focus on those. So anything, if you do that, you would see what's coming up soon. That's the way we do it.
Yeah, and that's a great hint to influence about for upcoming releases, just to post your issues to the community and it will be upcoming release.
Yeah. So we can see that it's running on the GK cluster as well. This is the IP address of the public load balancer. So you should be actually able to open that up in your browsers as well. So that's I think that's near the end. Yes. Let me just two more slides and then I'm done. Right, alpha or beta, as I promised. The Kubernetes provider currently supports all of V1 because it was just safe to implement for us. And we received many requests for alpha or beta resources like deployment or ingress. But the problem with alpha or beta is that there is potential for breaking API changes, and we need to figure out how do we deal with those without impacting the end user too much. So I'm aware that both Google and the Kubernetes community perceive alpha or beta differently to many other communities, and the APIs remain there for a fairly long time, and I respect that. And in fact, I thank Google for being so upfront about this. And I think the Google team that works on the GCP provider for Terraform came up with a fairly good solution in that area. So we'll probably apply that approach in this Kubernetes provider too, eventually. So to sum up, use DSL to your advantage because it's there, so you don't have to deal with YAML. This is mainly ops-focused provider, so be careful when running pods and controllers and things like that, and especially when running application workload through it. and think about your culture and workflows first before touching the configs, and be aware of who is in control of your Kubernetes resources and avoid the overlap if you can. So that's it. You can, if you want to file any issues or send PRs, you're certainly welcome to do that in here. And that's the end of my talk.
So I propose to make a short break, and then we'll just return back and have some kind of discussion. So.